Okay, so now we're starting chapter 6. The first thing we're going to cover is this notion of something called a vector field. Um, Vector fields are really useful for describing physical phenomena, force fields, things such as gravitation, electromagnetism. The idea is that at each point you have a vector. Okay, so that's really in the definition. A vector field is a way of assigning to every point in space a vector. Um, so in R2, two-dimensional space, you insert a point x comma y into the vector field f, and it will return back to you a two-dimensional vector. And a vector field in R3, you plug in a point x comma y comma z into the vector field, and it'll give you back a vector that'll be a three-dimensional vector. Maybe a slight technical point I want to emphasize here is that you don't have to have the assignment go in every single point in R2 or in R3. You can have places where the vector field is undefined. So that's why we say in a subset here. Okay, and there's an example coming up where we have such a point where the vector field is undefined. Okay. So now this is a rather simple notion. So a unit vector field is a vector field where each vector has unit length. So length 1. Okay. And, well, how do you get unit vector fields from just arbitrary vector fields? So if this is an arbitrary vector field PQR, these are the component functions that form the vector field. What you can do is you can normalize. Right? You can divide by the overall magnitude of this. So that's what that does. So an example, suppose you have, well, I guess I should say that we starting from f of x comma y is equal to, or maybe I want to use a different letter. Maybe I'll just say g. So starting with g of x comma y equals y comma negative x, right? If you take the magnitude of this, you end up with y squared minus y squared plus quantity negative x squared. So y squared plus x squared all in a square root. Right? That's taking the magnitude of g, and then that goes into the denominator, and so you end up with the normalized version, which is this. And so notice these two pictures. So the left one is this vector field g. You can see that the lengths of the vectors here are different. They get longer as you go further away from the origin. Whereas the one on the right, they all appear to be of the same length, and so that corresponds to f in this case. And this is what I wanted to point out also, that notice if you try to plug in 0, 0 into f, you get an undefined quantity, right? You can't divide by 0. So this vector field is not defined at the origin. Okay, so its domain is, I believe, is everywhere except the origin, in fact. Yeah, the things like this, there's it's going to be important to consider like the domain of a vector field as for certain problems, but not really for this section. This section is actually very easy, I would say. All right. Yeah. So now software. I should make a quick comment about software, of how you graph vector fields. So in case you want to use technology, uh, to do this kind of thing. Well, all of these tools are capable. Some of them you have to like put in the work to actually make it sketch things out. So that hopefully like there are other people that have made little GeoGebra notebooks or Desmos notebooks where it has all the code like sort of hidden in somewhere, and then you can just change the functions and graph the thing. Wolfram Alpha can do it, but probably it's simplest if you just use the Calc plot 3D. I didn't think to show that. Uh, yeah, I can show that. That's fine. Uh, uh, 1 second. Yeah. All right. Right. So from this, you want to, we'll turn that off and then open up vector field, and then you can change these quantities. You have to check this off. And so you'd get this. So this is kind of like 3D, but in order to make it really 3D, you have to change this. You have to say how many z coordinates you want to use. So if I say like 5, oh, that was not 5, that's 5, then it kind of does that. Everything is flat because the function p is nothing. So like if I say x times y, now it actually starts using the z direction as well. Notice that in this case we can kind of do something really um, sort of faking normalizing it. It just forces them all to be the same length. Um, and there's a nice way to restrict down to the two-dimensional view. Oh, and well, this is more useful for like PDEs or differential equations, like sort of showing the flow of a particle that is subject to this force field, I guess, this vector field. Okay, I guess that's good enough. All right, coming back to this. So, all right, where are we? Okay, so gradient fields. Yeah, so now this is another important concept to know. So, uh, there are special kinds of vector fields that are called gradient fields or conservative vector fields. So, uh, the word gradient is coming from the fact that these vector fields arise as the gradient of some function, as you can see here, right? So the fact that the vector field f is arising as the gradient of some scalar function little f, right, is one reason why we might call it a gradient field. In physics, these are, I think, more commonly called conservative vector fields, and that's because they conserve a quantity. I believe it's energy that they conserve. Yes, so energy is conserved, is what I wrote here. So, right. And I will typically opt to say conservative vector field because that's what I was taught. Uh, and this function little f, this scalar function has a name as well. It's called the potential function, which also is coming from physics. All right, so we have that. And more will be said about conservative vector fields in 6.3. We're just going to briefly touch upon this notion and then we'll revisit it and hash it out more. And yeah, just as a small remark, there's a bit of a sign convention thing going on with physics. Physics people, they for some reason want negative. In math, we will usually be using the positive version of this. Okay. Right, so now a natural question that you might ask, right? So we said that conservative vector fields arise as coming from a potential function. They're the gradient of a potential function. Well, what if there are multiple such functions that would give you, that when you take the gradient would give you the same vector field? Is that possible? Well, the answer is yes, but they are all related to each other. They differ only by a constant, is what this ends up saying. So if you have f and g be two functions whose gradients are give rise to the same vector field f here, then they f and g must differ by just a constant. Okay. So unique up to a constant, which is the same thing as integrals, right? So the antiderivative is defined up to a constant. Okay. Okay, yes. Now this is a nice property that conservative vector fields have. They satisfy the cross partial property. This is actually a very uh, direct consequence. It's really easy to see that this holds true. So it follows from the fact that, well, if we state that the vector field is conservative, then that means it's the gradient of a potential function. Let me just jump over to the proof here. So if f is conservative, then it's the gradient of a potential function, which means that these component functions, this p and q, p is actually little f sub x, and q is actually little f sub y. Okay, so you're taking the partial derivative. You're doing p sub x and q sub y. And then, well, the cross-partial properties are saying that you basically mix the partial derivative. So if this is the function in the x coordinate, that's the function in the y coordinate, then you use the other partial derivative. So you end up doing p sub y and q sub x. Okay. And so this is the cross-partial property in the two-dimensional case, and these three equations being satisfied would be the three-dimensional case. So seeing that, so I'm just trying to justify why we know that this must hold true for conservative vector fields. Well, if the vector field is conservative, then it's coming from a potential function little f. You take its partials, and then you notice that p sub y, which is this, would actually be f sub xy. And q sub x would actually be f sub y x. Right? This is the y derivative of little f, and then you take the x derivative of it. You get that. And these two are equal by Clairaut's theorem. Right? We assume that the mixed partials are equal, and the technical assumption there was that I believe it was the second derivatives are continuous. Yeah, which we can basically assume is true. So. And yes, for the three-dimensional case, it is also very similar. And let me just maybe talk through that as well. So the way that I think about it, I really think of P, Q, and R as corresponding to the component functions of like the X, Y, and Z kind of variety. And so these three equations you get by just picking any two of them and then like switching the letters. So P and Q correspond to picking the x and y components, and then you just switch the two. So you do p sub y and q sub x, and you get this equality. If we instead select y and z, q and r, that's these two, then notice that the cross partials property is saying q sub z is equal to r sub y, right, which is that. And if we select x and z, p and r, then the cross partials property says p sub z is equal to r sub x, which is that property there. So there we have it. That's why this is called the cross partial property. Later on, we'll see that this can be expressed in a different way involving an operation called the curl. But you'll have to wait till I think it's 6.5 for that. Okay. So continuing on. Right, so what we've found, what this theorem has stated is if f is conservative, then f must satisfy the cross-partial property. Now this does not say the converse, which is the statement f satisfying the cross-partial property implies that f is conservative. That is not true. You actually need an additional assumption. F satisfies the cross-partial property and also something that we'll cover later on, but I'll say it now. The domain that f is on has to be simply connected, which effectively means that it can't have any holes in it. Okay, so you need that additional assumption, otherwise the statement is not true, and it is not true for a very good reason. There's a very standard example that illustrates this converse not holding, which is this example here. So in this example, now what we can do with this example is we can show that it satisfies the cross-partial property, but we're not going to be able to show that it's conservative right now. We'll have to show that later because we end up needing a an additional property about conservative vector fields that we're not going to cover in this section. Okay, so I just decided to illustrate this just to show you that this is also this vector field looks really similar to this previous guy, except notice that this has a square root, right? So this has a square root, whereas this one, the signs are the same. It's still y and minus x on top, but you don't have the square root. You have a just the I want to say it's the magnitude squared of it. So this is like I think some people call this the radial vector field, but I'm probably forgetting terminology. Okay. Well, okay, anyway, so we can show that it satisfies the cross partial property. That's just straight up taking the partial derivatives. So I wrote it below. So you take the y derivative of this function, you take the x derivative of this function, and you compare the two. And that involves quotient rule, as you can see, because top and bottom of these functions, well, top and bottom of this have a y, so I have to use quotient rule. Top and bottom of this have x, so I have to use quotient rule. So then I wrote out all the steps for quotient rule, just in case. And when you do the quotient rule, you simplify the numerator, you end up with this, and you end up with this. And these two are clearly equal. So this vector field satisfies the cross partial property. But the issue for this is it's not going to be conservative. This vector field is not conservative. And I can't justify that here. We'll justify that in section 6.3. Yeah. But when we have that additional condition about like the additional assumption that I mentioned, where the vector field needs to be on a simply connected domain, this is not on a simply connected domain. Notice that this vector field is not defined at 0, and so that excludes this from working. I mean, technically, it doesn't mean that it is or isn't conservative either. At that point, you still need to justify that it cannot arise as the gradient of a potential function in order to state that this is not conservative. And we'll show it through a slightly different mechanism in 6.3. Okay, that's all I say about that.